Hello everyone, welcome back to my Journey Education YouTube channel. Today we are tackling one of the most classic data structures and algorithms challenges. It is reconstructing a binary search tree from its traversals. If you ever wondered how a computer saves a complex tree into a simple file and then brings it back to life perfectly, you are in the right place. This isn't just a theoretical puzzle, it's a fundamental concept, s- serialization, and a very common interview question at companies like Google, Amazon, and Microsoft. By the end of this video, you will master the logic and the optimized algorithm to solve the efficiently. Here is your roadmap. We will start with the foundation, making sure we understand binary search tree rules and the three types of traversals. Then we will dive into the reconstruction theory. Why certain traversals allow for unique tree while others don't. We will then compare two major algorithms, the naive recursive approach and the high performance range bound method. Finally, we'll do a detailed step-by-step trace using a real example. Let's start with the basics. Before we build a tree, we need to remember the golden rule of binary search trees. For any given node, every value in its left subtree must be strictly less than its value, and every value in its right subtree must be strictly greater. This ordering is what makes binary search trees so fast. For searching, it essentially allows us to perform a binary search in a tree format. When we reconstruct a tree, this rule is our primary constraint. When we flatten a tree into an array, we do it in one of three ways. First one is preorder. It is we visit the root first, then the left subtree, then the right. This is great for reconstruction because the first element is always the root. Second one is Inorder. It means left, then root, then right. This produces a perfectly sorted list. Third one is Postorder. It means left, then right, then root. Here the last element is the root. Keep these sequences in mind as they are the clouds we use to rebuild the hierarchy. Here is the cheat code for binary search trees. In a standard binary tree, the in order could be anything. But in binary search tree, the in order traversal is always a sorted array. Why is this important? It means if an interviewer gives you a pre-order sequence, they have implicitly give you the in-order sequence too. You just have to sort the Preorder array. This sorted property is the foundation of almost every reconstruction algorithm. Section 2. The theory of reconstruction. How much information do we actually need? In a general binary tree, one traversal is never enough. Why? Because you can't tell if a child is a left child or right child just by looking at the order. You usually need in order plus one other traversal. But for a binary search tree, the values themselves tell us where they belong. If the next number is smaller than the root, it must go left. If it's larger, it must go right. Because of this, a binary search tree can be uniquely reconstructed using only a pre-order or post-order sequence. This process of turning a tree into an array is called serialization. Bringing it back is deserialization. We do this whenever we need to store a tree in a database or send it over a network. Efficient reconstruction ensures that the data integrity, the search property, remains intact. Section 3. Let's look at our first approach. Algorithm 1. Naive regression. The algorithm uses a partial logic similar to quicksort. First one, we take the first element from the pre-order array. That's our root. Second one, we, we then scan the rest of the array to find the first element that is greater than our root. Third one, everything before that split point becomes the left subtree. Fourth one, everything from that point onwards becomes the right subtree. We then call this function recursively for both sides. While this is easy to understand, it has a performance flaw. In this worst case scenario, like a tree that's just one long line, we have to scan the entire remaining array at every single node. This results in a time complexity of O n to the power of 2 for a tree with 1 lakh nodes. This would be significantly slow. We can do better. Section 4. The pro-level approach. Algorithms to range bounds. Instead of scanning the array to find a split point, we use constraints. We passed a min and a max bound to every recursive call. As we move through the pre-order array, we only consume a number if it fits within the bounds of the current subtree. If a number is too big for the current left subtree, we simply return and let the right subtree attempt to take it. This means we only ever look at each number once. Look at this chart. By using range bounds, we move from O n to the power of 2 down to linear time of O. We were eliminated the redundant scanning. This is the most efficient way to reconstruct a binary search tree and is almost always the answer interviewers are looking for. Now let's see it in action. Section 5. The step-by-step walkthrough. We will use this pre-order sequence 10, 5, 1, 7, 40, 50. Note: 10 is the root. 5, 1 and 7 are the smaller than 10, so they will form the left subtree. 40 and 50 are larger, forming the right. Watch closely. 10 is the root. Its bounds are negative infinity to positive infinity. Next is 5. It's between negative infinity and 10. So it becomes 10's left child. Its new bounds are negative infinity to 10. Next is 1. It's between negative infinity and 5. So it becomes 5th left child. Next is 7. It's not between negative infinity and 1. So it's not 1's child. We backtrack 7 is between 5 and 10. So it becomes 5's right child. Continue the process. Next is 40. It's not between 7 and 10. It's not between 5 and 10. We go all the way back to the root. 40 is between 10 and positive infinity. So it becomes 10's right child. Finally, 50 is between 40 and plus infinity. So it becomes 40 right child. And here is our final result. Take a look at the tree. Every single node allows the binary search tree property. Left is smaller, right is larger. We will successfully reconstructed the hierarchy from a flat list in a single pass. Before you wrap up your study session, remember these three edge cases. First one is empty arrays. Your code should return null or none. Second one, skipped trees. Your algorithm must handle trees that look like linked list without crashing. Handles this best. Third one, invalid sequences. If the input array isn't a valid pre-order binary search tree sequence, your bounce check will naturally fail, allowing you to throw an error. That is how you reconstruct a binary search tree from its traversals. We will convert the why, the how, and the most efficient way to do it. If you found this step-by-step breakdown helpful, please hit the like button and subscribe for more deep dives into algorithms. If you have any question about the range bound logic, drop them in the comments below. See you in the next video. Thank you very much.